Hello, and thank you for joining us today as we here in America celebrate our Independence Weekend. But we do want to celebrate the independence of every country who picks some other day of the year to tell the man enough is enough. Today we're going to be talking about equivalent hydraulic conductivity. And what that means is essentially when you have a hydraulic formation that's usually sandwiched between clay layers, confining layers, that typically we want to express that in some equivalence that basically simplifies things, right? So when you have, let's see if I can use this. So when you have overlying layers of different hydraulic conductivities, typically you want to express the formation as just one hydraulic conductivity. And so how do we do that? Well, we can do that using equivalence, but there's two different ways of doing that. So there's horizontal and vertical hydraulic equivalence. And a question for you is, should say not I, but is vertical flow always vertical equivalence? So in other words, when you have flow going vertically through systems, is that always going to be your vertical equivalence? Can it sometimes be horizontal? Well, let's take a look. All right, so as an example, if you are familiar with groundwater hydrology, you're probably familiar with Henry Darcy, for example. So a lot of the work that he did involved test columns and packed columns. So he did work where he would take a column and he would pack it with porous media and basically flow water through it to equilibrium and then study how the water changed through the system. Well, what if you were to take that system and you were to use, instead of just one homogeneous packed column layer, porous media layer, what if you were to use multiple layered porous media of differing hydraulic conductivities, and then you flow water through it? How would you express this as one hydraulic conductivity? Would you consider this example as vertical or horizontal equivalence? And that's really important when it comes to understanding how to calculate these types of systems. So that would be an example of actually vertical equivalence, right? So we're looking at this as a horizontal flow, but it would actually be vertical equivalence. And the reason for that is because we are flowing through different layers in series. So the flow has to flow through each layer in series, one at a time, before it can flow through. But if we were to look at this as a horizontal flow, then it would have an option. If one layer has high hydraulic conductivity, then flow can have preferential flow through that type of media, right? So how we calculate this, if we're looking at vertical equivalence, now remember this is flow really not necessarily vertical equivalence, but flow in series. We call it vertical equivalence because in hydrology, obviously layers tend to happen, in layers, right? And when we talk about geology, everything happens in layers like this, unless you're on, the side of a mountain maybe. But that's why it's vertical or horizontal, but it actually doesn't matter, So if you're looking at a test cylinder, you need to be very careful about what type of flow it actually is, because I guarantee you, your professor or, on an FE exam or something is going to try to trip you up on that. Because actually the math is very simple. So if we look at vertical equivalence, So flow in series, right? So we have the total depth, and this could be, in this case, it's 2 layers, but it could be, as many as you want, right? But the total depth of however many layers you have divided by the sum of each individual depth times, or excuse me, divided by the hydraulic conductivity of that particular layer. So basically you're doing like a weighted average. All right, so that's how we do vertical equivalence. Horizontal equivalence is a little bit different. In this case, we are taking the depth of each layer times the hydraulic conductivity of that layer for each layer. We're dividing it by the total sum of the entire depth of however many layers it is and adding all that together. And so this is the kind of situation where, so say if K2 is very low hydraulic conductivity, so say it's, we're not really talking about clay layers here, but something like a silt maybe, where this is maybe a sand. So your flow basically, instead of flowing through K2, has the option of going around and flowing through K1. So essentially we're looking at, basically, we're limiting the depth of flow here, right? So a good question here, and one you'll probably see on your FE or maybe on an exam in your class, is if you look at the two, will the horizontal or vertical conductivity, equivalent conductivity, always be greater? Or does it depend on the type of aquifer you have? Well, it actually does not depend on the type of aquifer you have, unless you're separating things through clay layers or something like that. But if you're looking at a situation like this, a K1, K2 type of situation, where you're looking at equivalence of these two, then actually it's always going to be greater that you have horizontal. And the reason for that is because, like we said, if K2 is, say, not conducive, right, it has very low hydraulic conductivity, then you can flow through your sandy aquifer, through your aquifer of high hydraulic conductivity, your sandy aquifer, through K1, right? But if you're going vertically, so say K2 is something like a clay layer, or low hydraulic conductivity, then basically once you've flown through K2, it doesn't, or excuse me, K1, it doesn't really matter how conducive K1 is, because right, once you hit this barrier, it's all going to back up anyways, right? So whatever your lowest hydraulic conductivity is going to be your bottleneck in the system if you're going in series instead of in parallel, right? You don't have the option of flowing through parallel. Okay, so let's take a look at an example. So in this case, we have two homogeneous isotropic geological formations. And so if you're not familiar with those terms, hopefully you are. Homogeneous basically means if you pick any spot anywhere in this formation, it's going to be equivalent, right? There's no difference between different spots. Isotropic means there's no difference in direction. So vertical or horizontal doesn't matter. It's going to be the same. Okay, so these two are homogeneous isotropic. They're 10 meters thick. They overlie one another. So they have hydraulic conductivities of 10 to the negative 4 and 10 to the negative 6 meters per second. That's relatively common, relatively normal values. So what we want to do is calculate the horizontal and vertical components of hydraulic conductivity for the equivalent formation. Okay, so in this example, we had a system that had two layers, each were 10 meters, and we had one that was 10 to the negative 4 meters per second and 10 to the negative 6 meters per second. Okay, so our vertical conductivity equivalence, now remember, in this case it's obvious, right? But it'd be flowing in series. we will have d over the sum of d layer divided by the hydraulic conductivity of each layer, which is going to be 20 meters divided by, let's see, 10 meters divided by 10 to the negative 4 meters per second plus 10 meters divided by 10 to the negative 6 meters per second, right? And that comes out to be 1.98 10 to the negative 6 meters per second. Now, does that make sense? So, as we've said, basically, well, we didn't exactly say this, but you would expect that your hydraulic conductivity is going to be somewhere between these two layers, right? So it can't be lower than 10 to the negative 6, and it can't be higher than 10 to the negative 4. It's going to be an average between the two. But since 10 to the negative 6 is the confining layer, it's essentially the bottleneck between the two, you would expect it to be close to 10 to the negative 6, and it is, right? So you can travel through this layer quickly, but then when you hit this layer, it backs up, right? So essentially you're limited by your 10 to the negative 6 layer. All right, so let's take a look at your hydraulic conductivity. So this would be the example where you're traveling in parallel. So in this case, you have the sum of your individual layer times the depth of that individual layer divided by the total depth. So in this case, that's going to be 10 meters times 10 to the negative 4 meters per second divided by 20 meters plus 10 meters again times 10 to the negative 6 meters per second divided by 20 meters, right? Total depth. So in this case, your, I don't trust the eraser, so I'm just going to scribble over that. Your horizontal conductivity is going to be 5.05 times 10 to the negative 5 meters per second. Now, does that make sense? Well, it does, because in this case, basically, you're hitting this layer and going, nope, and you're coming over here and going through the more conducive layer, right? So basically, it's more of an average between the two. Essentially, what you have is, instead of having 20 meters, you have 10 meters of this hydraulic conductivity, plus a little bit more, if you were to consider that an equivalence, is kind of how I look at it. So, okay, well, that is the example for today. I hope that was helpful for you that may be preparing for the FE exam or any other kind of work that you're doing. So, thank you very much for joining us today, and good luck on your exams.